Okay, let's continue our discussion. But before I continue to chapter number, 28? I forgot to talk about the electric dipole, or a dipole in the electric in a uniform electric field. Remember when we had a dipole and placed an electric field, uniform electric field like this, then the forces are going to be like this. And because of the existence of these two equal and opposite forces, then this will rotate. And if it rotates, anything that rotates, we have to use any system that rotates, then we must describe it using torque. And torque, if you recall, F cross R. And F being equal to QE, so Q cross R. That's the torque, or when you have two charges, or a dipole, I should say, a dipole placed in a uniform electric field. From here, make sure that you go back to page, I believe it's page 711, and make sure you understand the formula associated with this, especially these two formula. One of them, which is basically, it says that torque is defined as P cross E, right? And P is the dipole moment. It's equal to Q times E. Okay, so make sure you you understand that, and then only you know how to calculate that, and then from that we calculated the electrostatic potential energy for a dipole, which was equal to P dotted with E. Okay, so P dot E minus P dot E, and both of these are vectors. So please make sure you go back and understand all of these things before I just forget to mention these, and these are very important. Of course, D in this case is simply the distance between the dipole, or between the two charges of the dipole. So please don't forget that. Okay. Now let's go back to chapter number, I believe, 28. Let me just flip over to chapter 28. Which talks about calculations of the magnetic field. So chapter 28 is calculations of the magnetic field. So it's basically calculating B. How do we calculate B? We had two ways. One way, which is basically the integral way, and I said we should not worry too much about the math, but using the Boyd-Savart law, in which we calculate B as mu naught over 4 pi, and then we have QV cross R hat divided by R square, or if you want, it's the same thing as mu over 4 pi IL cross R hat divided by R square. Whether you use Q or use an QV or an IL, depending on if you're talking about a charge moving with some speed V, or a current moving, or charges moving in a wire. So they give us current in the length, and L is the length of the wire. So that's one way. And remember, we said this, or at least I said in class, that this is tedious, and this may be a little bit, it needs to integrate, especially if you're doing the. Let me just write that down. I dl cross R hat over R square. If you're doing this, where you calculate the magnetic field over an infinite one, it doesn't have to be an infinite, but a conducting a wire or a conductor over which the current is distributed uniformly over that. So you can do that also, and we use this to calculate the current in a wire, in a ring. We used this formula to calculate that. But as I said, I mean, we did not, this is the Boyd-Savart law, but we did not, go into detail of calculating the calculations of B. But what we came out from that, we came out with a very important formula, which we used a lot, which is the famous one. There's it mu naught over 2 pi and I over X. And if you recall, this is the current due to a wire. So a wire carrying some current I, and the length of the wire is L. And this is the magnetic field at some point B, or some point P away from the wire, and and it's, as you can see, it only depends on the distance x. Okay, and we determine the direction of the magnetic field at this point using the right hand rule. In this case, it's into the page, and that's what. So it should be like this. That's what the magnetic field should be at this point if the if the current is this way. Okay. Now, why do I say this is important? Because we use this in the examples that are on pages 930 and 931. Right. So pages 930 and page 931, where we calculated the force, and this is very important. We calculated the force of one conductor on the other. Okay, so if I have a conductor carrying a current this way, I, and another conductor carrying a current this way, and I wanted to know the force on, let me call this 1 and this is 2. So we want the force due to 2 on 1. So how do I do that? The way I do that, by first calculating B due to 2. So I calculate B using this formula here, and it is this B here. Once I calculated B due to 2, then I come and I say, okay, the force due to 2 is equal to I1 L1 cross B2. Okay, and that's how I do that. And that's why this formula here, or this is very important. And we did, as you see, I think on page, as I said, pages 930 and page 931. This is very important, especially the example on page 930. So make sure you understand that, and make sure you understand how to calculate the force due to one wire on the other. Especially if you flip one of them is negative this way, then that's going to change. If the current one of them is negative, then it's going to change because the field here is going to be there. So in this case, the field is out, but if it is down, the field is in. So you have to be careful using your right hand rule. Okay, so that's the first part of chapter 28. The second part of chapter 28, which is again very important, which is it talks about the Boyd-Savart law. Okay, the Boyd-Savart law, it says that, Ampere's law, not the Boyd-Savart law. Ampere's law says that B dot dl is equal to mu enclosed, mu naught I enclosed. Okay, now this is Ampere's law. Ampere's law. Now we use this to calculate three things, and this is the one that I want you to be really careful with, is that we use it to calculate the current through a wire, okay, using Amperean integral as a circle, and we used it to calculate the current in a solenoid, and where we found the current inside the solenoid is uniform, but